We're in Physical Chemistry, Chapter 12, Section 7 now. In this section, we're going to talk about two-component liquid equilibrium. Now, the first definition is miscible, M-I-S-C-I-B-L-E. Two liquids are completely soluble in each other. So that's what miscible means. Example would be like water and acetone. In any ratio, they'll completely dissolve each other. Water, of course, is H2O, and here's the diagram for acetone. So what would it be? C3OH6, whatever. So likewise, if you have any alcohol with low molecular weight, MW is molecular weight, and water, those two will also be completely miscible. So that's why actually adding acetone, it'll dry out a container faster because the water will dissolve in the acetone. The acetone is more volatile, so the acetone evaporates, takes the water with it. So let's also talk about partially miscible. So that means that the two liquids, they're partially soluble in each other. For example, let's say we have N-pentanol in water. At the OH end of the pentanol, that is obviously hydrophilic, but the chain is hydrophobic. So here's a diagram of temperature versus mole fraction. So we have 0 to 1 of the A, substance A, and then 1 to 0 mole fraction of B. So you notice above this temperature, they're completely miscible. There's only one phase. But low enough temperature in just the right mole fraction, or well, let me put it this way. If you have pure substance A, or no, this would be pure substance B, or just a little A, they'll still be completely miscible at any temperature. We're talking about liquid only, remember. And likewise, if you only have pure A, or just a small amount of B, they'll be completely miscible at any temperature. Again, we're talking about only the liquid phase. But most lower temperatures and pretty much any mole fraction of A and B, then you're going to actually have two phases. Now, I didn't explain what those phases are yet. Don't assume yet. Now, this temperature up here, the highest temperature, capital T subscript C, that's called the critical temperature, or the upper critical temperature, or the critical solution temperature. So that's the highest temperature that you can have two phases. So L1, where are we? This lever line 1 is going to be C to D, and this linked line 2, D to E. And then again, using the lever rule we had before, the number of moles of A plus the number of moles of B times the length of 1 is going to be equal to the number of moles of A plus the number of moles of B times the length of 2. Now, where there are two phases, that's when the lever rule applies, or the lever rule. Now, if you have two substances, that's when you have two substances that are in equilibrium with each other. Now, let's talk about a water and a tertiary amine. So we have water and this C2H53N. So we have the mole fraction of the amine going across here. So we have pure amine or pure water over here. Notice here we have a lower critical temperature. In this case, the example is 20 degrees Celsius. This is because of hydrogen bonding. And of course, above this temperature, you have two phases. Below this temperature, you have just one phase. Now, on the other hand, there's water and nicotine. Here, so right in the right region of mole fractions and temperatures, you have two phases. At really low temperature or really high temperature, you have one phase. And of course, if you have really low concentration of either, you have just one phase. So in this case, we have an upper critical temperature. This is due to entropy. In this case, we get temperature times the change in entropy is going to be greater than the change in enthalpy. And then down here, we have a lower critical temperature. And then nicotine is an alkaloid, by the way. Now this two-phase region in here, this is called the miscibility gap. Now other examples would be like helium and xenon, or ammonia and methane, or carbon dioxide and water. That is all we're doing for Section 7.